Okay, good afternoon, all of you. Welcome to this ninth lecture of refrigeration and air conditioning. Today we are going to discuss about pH diagrams, pressure and enthalpy diagrams, which are very important in order to understand the various processes inside a refrigeration systems. So before going to that, I want to again tell you that I have already shared that study material sheet with you. So those who had missed previous lecture, so we had given a link in that sheet. You can click on that link and you can watch those videos again. Okay. So I'm trying to update that sheet. So up to now, whatever lectures are being there conducted by several teachers, POM, AC, OR, and ED. So I'm in touch with them. I will try to uh, I'll tell them to add all the links for video lectures or notes or MCQ, whatever it is there. So in my sheet, in that RAC sheet, so I have shared links for books also. So two books I have shared in that. First is by R.S. Kurmi, Refrigeration and Air Conditioning, which is academic book, and second is a foreign author book by Miller. So that is a kind of industry-oriented book. It is related to like applications. So R.S. Kurmi book, it talks about concepts, and that another book by foreign author, it talks about the industrial applications of this concept. So please check that study material sheet, and if you want more in that class notes or PPT or external resources, we'll try to add that also. Okay. So I think we'll start today's lecture. So we are in first chapter, that is basic refrigeration cycle. Uh, we have discussed reverse Carnot cycle, Bell-Coleman cycle. We have taken derivation and numericals based on Bell-Coleman cycle. Last lecture we have studied the air refrigerant cycles. So we have studied very advanced subject yesterday. That is a refrigeration system. Sorry, the aircraft refrigeration system. Okay. So in that we have studied like why refrigeration is needed in aircrafts. So because of the atmospheric conditions at the higher altitudes, we need a refrigeration for the occupants. We have seen the various types in it. So like a simple air cooling system, bootstrap system, reduced ambient system, and regenerative air refrigeration system. So all that we have studied, and also we have seen the advantages and disadvantages in the previous one lecture before. Okay, so that is all about air refrigeration system, where air is used. Why they are using air? Because air is free. Like we don't have to pay for air. Air is free and it is available in huge amount. We can take as much we want. But the thing is that the COP is less in air refrigeration system, and because of that, we go for other refrigerants like R22, R12, ammonia. So these are some commercial refrigerants we are using. The thing about these refrigerants is that their boiling point is very low. So like if you take room temperatures of 30, 35 degrees Celsius, they boil at these temperatures. Okay. So it is not day-to-day phenomena, because if you take water boils at 100 degrees Celsius. But if you take any refrigerant, it boils at very low temperature. Uh, so that's why they are used for low temperature applications. And speaking about the temperature, first I want to clear this misconception about temperature. Okay, so it is said that if a body is at low temperature or high temperature, that we can feel by our hands. Okay, so if I take a metallic object in my one hand, and if I take a book in my other hand, okay, so you can try that now also. You take any metallic material nearby you. If your mobile is having that metallic panel, that is also okay. Or and in other hand, you can take a book. Now, if I ask you like which one is having more temperature or which one is having less temperature, so common answers we get it as like a metal. That metallic part is at a lower temperature and book is at higher temperature. So those who are doing that right now, they can relate to this. So if you take a metallic object in one hand and a book in your other hand, okay, right now, and if I ask you which one is having a higher temperature, you will tell that sir, book is at higher temperature because it feels warm to you, and you will tell that the metallic object is at lower temperature because it feels uh, cool to you or cold to you. Okay, but if you apply the logic, both are at the same temperature, that is the room temperature. Both are having at the same temperature. Still, you feel that one object is at higher temperature and another is a lower temperature. You feel that one object is warmer and another is colder. Okay. So there is a misconception about this temperature. So what is actually happening is that so I'll draw that here. Okay. So suppose this is your hard drive of metal or any object of metal, and if I take book, okay, suppose this is your book. Okay, now if I tell to touch one of these, like I told previously, you will feel this is like cooler and this is warmer, but temperature of this object T1 is equal to temperature of this object T2. So what is happening in this case actually? So here the term thermal conductivity comes into picture. So thermal conductivity of metal is higher than thermal conductivity of the book. Okay, so K1 is greater than K2. So we all know that the rate of heat transfer is directly proportional to this thermal conductivity. So like what is happening that when you touch this object, whatever heat transfer is there, suppose it is Q1, and if you touch the book, in that case, the heat transfer is Q2. So in that case, what is happening? Q1 is greater than Q2. So more heat is being transferred from metal to your body, and less heat is transferred from book to your body. So that is why you feel that metal is like, kind of cooler or cold, and you feel the book a little bit warmer. So that concept is related to the heat transfer. Okay, so though they are at same temperatures, but the heat transfer is different. So that is why there is a difference between what you feel when you touch those objects. Okay, so I think I have cleared this misconception about temperatures. uh, so we don't so up to like this stage we have assumed that there is some temperatures define which one is cooler, which one is warmer, but it is actually the heat transfer rate that determines this situation, okay, or this phenomena. So that is the start. uh, Now we'll move towards our topic of today. Okay, so today's topic is pressure enthalpy diagrams. In short, they are also called as pH diagrams. So pressure, as you know, it is force per unit area. Okay, pressure, as you know, this is a force per unit area, and enthalpy, as you know, that is energy in flow. So that is nothing but energy in flow. If there is no flow, that energy we call it as internal energy. So whenever that energy we take in flow, we call it as enthalpy. Okay, so if I draw pressure versus enthalpy, I get a pH diagram. Okay, so as you see on the screen at right side, there is one graph. It is shown there. It is like pressure versus enthalpy, and one curve is drawn. Okay, so one curve is drawn. So this locus is what we are interested now. Okay, so from diagram you can say that whatever lies inside the locus, so that is a two phase. If I take water, that will be water plus vapor, liquid water plus vapor, so liquid plus vapor. If I take a left to that curve, so that will be in liquid. Okay, if I take a right to that curve, so that will be vapor. So here it will be liquid water, here it will be steam. So this diagram you have already studied in basic, not the basic, applied thermodynamics, where you have to calculate work done for thermal power plants. In that, we have studied Rankine cycle. Now we are going to study vapor compression cycle. But that diagram will remain same. That is pH diagram. So what it says, we'll see. So I'll read whatever on the screen. So the most convenient chart, it is the most convenient chart for studying the behavior of a refrigerant is the pH chart. The vertical ordinates represent pressure and the horizontal ordinates represent enthalpy. So this vertical thing, that is the pressure. So if I draw horizontal lines, so what will be there? There will be constant pressure lines, okay? And the horizontal ordinates, these are enthalpy. So if I draw vertical lines, so those will be constant enthalpy lines. Okay. Moving on, the chart is divided into three areas which are separated from each other by the saturated liquid curve and saturated vapor curve. So what you see on the left side, this part we generally call it as a saturated liquid curve, and this part we call it as a saturated vapor curve. But the question is how we get this curve. Like, so like it is not that I had a dream. In my dream, one scientist came and he told me that the pH diagram looks like this. It is the shape. So it is not like that. Okay, so there is some method to draw this pH diagram. You might have studied in this in your applied thermodynamics, but like what I feel that before you graduate, you should know the basics. So I will tell you that again. Okay, so you ready? So we'll take example of water. So we'll take example of water, and let us assume the pressure is 1 bar, right? So pressure is 1 bar. I will draw that pH diagram. Right? Oh, let me put some markings. So let us say this is a 20, 40, 60, 80, 100. So like this is, let this be a temperature, okay? So temperature versus enthalpy. Based on this, we can draw the pH diagrams also, 120, 140. Okay, and let us assume our water is at now 20 degrees Celsius. So here it is our water. So water is now at liquid phase. Okay, so this is your liquid water. So it must have some enthalpy. Okay, so let us assume this is a 0.1. So this is the enthalpy associated with 0.1. Now what I will do, I will increase the temperature of water. So let us say this is 1 kg of water. 1 kg of water, that means 1 liter of water. So 1 kg of water I have taken in liquid stage, which is at now 20 degrees Celsius. So let us this be in 20 degrees Celsius, enthalpy in kilojoule per kg Kelvin, right? Now what I will do, I will increase its temperature. So I will increase its temperature. Okay, I'm increasing. So increasing the temperature, that process what we call it as a sensible heating. Now it goes to a temperature. So we know that at 1 bar pressure, the boiling point of water, it is 100 degrees Celsius. So I will stop here. So I reach to a point 2. Now what is point 2? It actually what we call it as a saturated liquid point. So what is happening at this stage? From 2 onwards, the water will change its phase from liquid to vapor. Okay, it will change its phase from liquid to vapor. And what is happening here? So let us say this enthalpy at point 2, it is H2. So whenever there is a phase change, as we know that temperature remains constant, but energy is being added, and that energy required to change the phase, we call it as a latent heat of vaporization. If it is changing from liquid to vapor. So let us say this is 0.3. So what is happening here? I have added some amount of heat. Okay, so this much amount of heat I have added here. So this much amount of heat, what we call it as a latent heat. Okay, so latent heat is added. And now what will happen? We are reached to 0.3. What is the 0.3? 0.3 is the saturated vapor condition. So 2 was saturated liquid. Now 3 is saturated vapor. Now water is converted 100% into vapor or steam. Okay. Now if I increase temperature again, what will happen in this case? This temperature will increase. Okay. And this phase, what we call it as a superheating. So if I go here 0.4, so 0.4 is the superheated state. Okay. 0.4 is the superheated state. Now, this condition applies for 1 bar. So this is for 1 bar. If I increase the pressure, if I do this same process in higher pressures, what I will get? So I will get like this. So if I take here and okay, so okay. So what will happen? It will go to this point. So this is at another pressure. Let us say this is at 2 bar. So at 2 bar again I have here 1 dash, I have 2 dash, and then there is a latent heat is added. So I will reach to 0.3 dash. Okay. Then again I will reach, if I increase the temperature, that will be 4 dash. Okay. Similarly, if I increase the pressure, now this was related to 2 bar. Okay, now if I follow the same procedure for a higher pressure, let us take a higher pressure of 10 bar. So I will go from like again 1 double dash, I will reach to 0.2 double dash, I will reach to point let us say here. Okay, 3 dash. Now why I am reducing this length of latent heat? Because the latent heat reduces as the pressure increases. So latent heat, that is the heat required to convert liquid into vapor, it reduces as the pressure increases. Okay, as the pressure increases. So I'll reach to 0.3 dash. If I 3 double dash, if I increase the temperature, it will again reach to 0.4 double dash. Okay, now see closely. If I connect all these points, okay, if I connect all these points, I will get a curve. Okay, I will get a curve like this. Again, so this curve, what it connects is saturated liquid points. So this curve connects saturated liquid points. So wait, I will choose another color for this. Let us say green. So if I join all this saturated liquid point, I will get a curve. So this curve, what we call it as a saturated liquid curve. Okay. Again, if I join these saturated vapor points, so I will get another curve. So this will be, sorry. So this will be like this, and it will come downwards. Okay. So this will be called as saturated vapor curve. So just quickly I will write here saturated vapor curve. Okay. So this is how I will get similarly in case of pressure. If I replace this temperature, I have just shown it for the understanding purpose. So this way I will get a pH diagram also. So whenever this saturated liquid curve reaches to a point where it coincides with the saturated vapor curve, this point we have to call it as a critical point. So this is the critical point. Okay. So this is a critical point where these two saturated liquid curve and vapor curve, they coincide. So I hope you have understood the process. We started with 1 bar. Then we followed the same process for different pressures, and ultimately we got number of saturated liquid points, number of saturated vapor points. We obtain a locus, two locus we obtain, and if I join this two locus, we'll get a critical point. So that is how we get this diagrams for different pressures. So that is what is shown here also. So if you see this diagram, this is a pH diagram, and here you will get a critical point. So this point is critical point. For water, it is around 22 megapascal. That is the pressure at which it reaches to its critical point. And this curve, whatever left of it, it is a liquid. Whatever right side of this is, it is vapor, and inside what we call it as a wet mixture. Okay, so this is called as wet mixture. Why wet mixture? Because it contains both liquid and vapor, right? So this is the simplest pH diagram. We'll move towards a little bit complicated diagram. Okay, so this is a little bit complicated diagram, what you see on the screen. So it is again a pH diagram, pressure versus enthalpy diagram. And it has a saturated liquid line. So see here, if you see, this is a saturated liquid line. It goes up, then here on the right side we have a saturated vapor line, and at this point what we get, it is a critical point. Okay, now they have shown here that so the corresponding pressure, it will be critical pressure. Okay, so whatever whatever left of saturated liquid line, that is a subcooled liquid region, and whatever right of it, it is a superheated vapor region. Okay, so this is very important. So there are three regions: subcooled region, superheated region, and whatever inside of that curve, that is nothing but wet vapor region. That is nothing but wet vapor region. So there are three regions: subcooled, superheated, and wet region. So these three areas what we get if we draw the pH diagram. Okay, so I want you to draw this diagram uh, because things will get a little bit complicated from this point onward. This is the simplest diagram we will get. Okay, so please draw it. So Rohit is asking me what happens if we heat steam above 0.4. So 0.4 is not the end of the line. Okay, 0.4 I have taken just in between the process of superheating. So it can go beyond also, like it can go 0.5, 0.6. Okay, so that way it happens. What happens in generally, the enthalpy increases. So here maybe some enthalpy we have got, maybe H4. Okay, so that enthalpy will increase. The interesting thing here, it is critical point. So what happens at critical point? There is no latent heat is added. Okay, so if you increase the temperature of water at 22 megapascal, that time what happens? There is no latent heat is required. Directly that liquid is converted into steam. Okay. So don't draw that dotted lines 1, 2, 3, 4. That is actually vapor compression cycle, but that we'll see later. So left, otherwise all other things, this curve and pH graph that you can draw. No need to draw that dotted line 1, 2, 3, 4. So I hope all you have drawn the diagram, and I can move further in this topic. Okay, so this was the explanation for it, and I will read this. So points falling on the saturated liquid curve represent the saturated condition of the liquid at that pressure point. So whatever point lies on this saturated liquid line, if I take this point, these are all saturated liquid points, but at different pressures. Points or area to the left of the saturated liquid line represent subcooled conditions of the liquid. So that area to the left, it is subcooled liquid region. Similarly, the area on the right of the saturated vapor curve represents the superheated condition of the vapor. So whatever right of the saturated vapor curve, that is a saturated vapor line or saturated vapor region. So no need to draw this. We already drawn the last diagram. Some curves are here which are shown in the diagram. So first one is constant volume diagram. So this center line, whichever where you see. So these are the constant volume curves. So this curve and this curve and this curve. So these are the constant volume lines. Then we have constant temperature lines. So whatever you see here, these lines, vertical lines here you see. So those are the constant temperature lines. Then we have constant entropy lines. So that is the dashed line. So whatever you see here on the right side, so these curves, these are nothing but constant entropy lines. So in previous diagram, you can show these lines, constant temperature, constant volume, and constant entropy diagrams. So that will be like this. So this is a standard diagram for R22. R22 is one refrigerant. Okay. So this is its pH diagram. Whatever you see here on this abscissa, sorry, ordinate. So that is the pressure. This is in PSIA. So that is a pounds per square inch absolute. So this A stands for absolute. And what you see on this x-axis, so that is enthalpy in BTU per pounds. Okay. So this is enthalpy in BTU per pounds. And this diagram here, it is a pH diagram. So as you see, there is a saturated liquid curve. Temperature is given in degree Fahrenheit, and here we have a saturated vapor curve. Okay, and they all meet at one critical point. So there is one critical point here, where that after which the pressure, you can see it is reducing. So this is your critical point. So see here. So whenever a question will be asked in your exam to draw the pH diagram and explain it, first you have to draw this two coordinates, that pressure versus enthalpy. Then you have to draw the saturated liquid curve, vapor curve, critical point. Critical point is not necessary. You can draw these two curves. After that, you have to draw. So whatever you see on the right side, so there is a constant temperature curve. So these are the vertical lines, constant temperature curve. Then we have constant entropy lines. So this curves going in upward direction. These are the constant entropy lines. Okay. So these are horizontal lines, that will be constant pressure lines. If I take a vertical lines here, that will be constant enthalpy lines. Okay. So in your previous diagram, add these curves, constant temperature curve, what you see on the right side, and constant entropy curves. Okay, so I hope you have added these lines in your previous diagram, constant temperature and constant entropy line. So that will give you a general idea about the pressure and enthalpy charts. Or in general, they are also called as Modier charts. So you might have heard this name Modier charts by Professor Gaudi sir in your second year of engineering. Modier charts, right? So pressure enthalpy charts curve or Modier charts, both are one and the same. Okay. So there is a one book, which is a very small book, like a log table book. It is called as a refrigerant and psychrometric properties, which contains all these pH diagrams and all the values for various refrigerant. So refrigerants, as it is mentioned on its cover book, R717, R11, R12, R22, R502, and eco-friendly 134A. So all this data for this refrigerant, it is compiled inside this book, and also the pH diagram for individual refrigerant is given. So for example, I will take R12, okay, and we'll see its charts and its tables. So if this lecture was conducted in classroom, it would have been better, because each and everyone will have that this book, and you can readily see it. But you can search on Google for its soft copies. If I find, then I will share with you all, because it is very important. In industry, they refer these values only if you want to design one system. So like it depends on the refrigerant. If I want to design a system working on R22, then all the pressure and temperature values I have to take from these tables. Okay, so I cannot randomly take any pressure and any temperature values. I have to refer to these values. Then I have to design a system. Okay. So for a reference, I will show you the R12. Where is R12? Yes, here it is. Okay, let me just go into. Okay, I hope you all can see. So see here, this is the table for R12, which is also called the difluoromethane, CCl2F2. So that is refrigerant R12. Properties of liquid and saturated vapor. So this is a section for R12. So see the table carefully. So here you have temperature, then there is a pressure, then you have enthalpy. So under enthalpy, there are two values. One is HF. HF is the enthalpy of saturated liquid, and Hg is the enthalpy of the saturated vapor. So difference between Hg and HF, that will give you the latent heat. Okay. Then next column is entropy. Under entropy also we have SF, that is the entropy of saturated liquid, and we have Sg, that is the entropy of saturated vapor. Then last column is the specific volume, meter cube per kg. So we have Vf, again same, specific volume of saturated liquid, and then we have Vg, that is the specific volume of saturated vapor. Okay. So I will read the first value, that is minus 60 here, what you see. So at minus 60 degrees Celsius, the pressure it is 0.2262. Its enthalpy is 146.46. Entropy is 0.77. Okay. Specific volume is 0.63. Now we all know by third law of thermodynamics that entropy reaches to its value 0 at absolute zero temperature. So absolute zero temperature, it is 0 Kelvin, that is minus 273 degrees Celsius. But at minus 60 degrees Celsius, it has some value that is in 0.77977. Okay. So likewise, we have other values also. Okay. So see here at 0 degrees Celsius. So I'm interested in this. So at 0 degrees Celsius, it has the pressure of 3.08 bar. So pressure is in bar. It has a HF, that is 200 kilojoule per kg. Okay, and it has other values. So same chart it is shown on the diagram also. So I'll show the diagram also. So this is the diagram what you see on the screen. So on the y-axis we have pressure, on the x-axis we have enthalpy, right? And we have this saturated vapor, saturated liquid line here, and what you see here, that is a saturated vapor curve. Okay, so we have two curves, saturated liquid and saturated vapor curves. On y-axis we have pressure, on x-axis we have a enthalpy. So don't get scared or don't get nervous by seeing the diagram. It is just a representation of the chart which I showed just above. So here I told you that I see a value that at 0 degrees Celsius I have enthalpy at saturated liquid as 200. I'll check if it is true. Okay, so I'll take yes, here it is, temperatures are mentioned minus 30, minus 20, minus 10 and 0. So at 0 degrees Celsius I will check the enthalpy. Now where is the enthalpy? I have to come straight down here. So I can see it is a 200 kilojoule per kg, which is true. Now if I read this diagram correctly, so at 0 degrees Celsius, if I take a horizontal line, I will get the value of pressure also. So pressure value is given as 3.00. Okay. So this is not exactly 0, somewhat below of 0, but approximately I have taken 0. So I will check in that chart if the at 0 degrees Celsius its pressure is 3 bar or not. Okay. So at 0 degrees Celsius its pressure is 3.0861. Okay. Because here that the point, that intersection point is just somewhat below of 0. That is why we are getting that greater value, right? So this is about left side. If I come to the right side, just I showed you the vertical lines, those are constant temperature lines. Okay, the inclined lines, those are the constant entropy lines. Okay, and dashed lines, these are nothing but constant volume lines. Okay, so these are the constant volume lines, constant entropy lines, and vertical we have constant temperature lines. Okay. So if I take R12's, if I hit R12 at 1 bar, see at 1 bar its saturation temperature itself it is minus 30. Okay, at 1 bar its saturation temperature it is minus 30, and enthalpy it is like between 160 and 180. That is nothing but you can take it as approximately 170. Then I have to heat this liquid R12 into to convert into vapor R12. Okay, so I have to add this much latent heat. How much? I have to go from 170. So here it may be approximately. So here it is approximately 340. Okay, so you have to double the value. So here it enthalpy at minus 30 it was 170. kilojoule per kg. If I add that much amount only, 170 plus 170, 340. So at 340, I will get a vapor R12. Okay. So now liquid R12 is converted into vapor R12. If I increase this temperature from this onwards, I will get a superheated R12. Okay. So the left side of saturated liquid, that is a subcooled R12. In between, we have a wet R12. Now on the right side of the saturated vapor curve, so right side is nothing but superheated R12. Okay, so I hope you are understanding this diagram. So previously we had a very simple diagram of pH diagram, and then we saw that this table for R12, properties of liquid and saturated vapor, for different temperatures it has different pressure values, enthalpy values, and entropy values, and specific volume values. Okay, so this was up to 3 bar. I will take more values. So more values means I have values from 4 bar, sorry, not 4 bar, sorry, 4 degrees Celsius. Then I have values up to our room temperature. Okay, let us say our room temperature, it is 30 degrees Celsius. So at 30 degrees Celsius, its saturation pressure, that will be 7.449 or 7.45. So this will be its entropy, saturation liquid, entropy of saturated vapor. This will be the entropies. This will be saturated vapor lines. Okay. So let me just add a comment line. Okay, so I'll take this value. So this will be my values. If I take 30 degrees Celsius, at that time R12's pressure, it is say 1.45. So these two are again enthalpy values. Okay. Then these two are its entropy values. Then these two are again its specific volume values. Okay. So I hope you are understanding what I am trying to dictate here. So we have studied the pH diagram, and now I am showing the pH diagram for the R12. Okay, any doubts? So those are having this, those like if they can get Amazon parcel, so this book may be available on Amazon, so you can order it. It will be delivered. Okay. For air, we don't have pH diagram. For air, what we have, it is a called as psychrometric chart. So this book contains both pH charts and psychrometric charts. Psychrometric charts we'll study in section 2. But for refrigerants which are commercially available, we have pH charts. From pH charts, we'll get different values. So if you are going to solve the numericals, we'll need this table. So I know in this period you can't have this book. If you can get, that is a great thing, but many of you will be not able to get this book. So whenever we are solving the problem, I will open this book, okay, scan book, and then we'll take the values from the table. So don't worry about this. We'll solve the problems together, right? So this is similar to what we had as steam tables in your second year of engineering. So in that you use the steam tables, and you calculated the enthalpy values. Then you might have calculated the X value. So X stands for dryness fraction. So whenever you are between under this diagram, so between saturated liquid and saturated vapor, so you get that just new to these things. Okay, wait. So whenever in between saturated liquid and saturated vapor lines, here you will get a wet vapor. Okay, so wet vapor means it has partially liquid and partially vapor, and we have to calculate the dryness fraction. So you might remember that you applied thermodynamics, you solved that problem, dryness fraction. So that also we'll see how to calculate the dryness fraction. Okay, but today's main focus is to understand first this pH diagrams. Once you understand this pH diagrams, solving problems is not a big deal. Okay, now I'll move towards the presentation. So I request you, if you can buy this book. If you don't have, then I will use my scan copy. Okay, so we'll see the processes on pH chart or the molecular chart. First is condensation. So condensation, as you know, that is when the vapor is converted into liquid. That process is condensation. Second is evaporation. Evaporation is when liquid is converted into vapor. Third is subcooling. So subcooling, as we know, if we cool the liquid, saturated liquid, again reduces temperature. That is process is called as subcooling. Superheating means if I increase the temperature of saturated vapor, so that will be superheating. Latent heat of vaporization. So if you are converting liquid, saturated liquid into saturated vapor, you will need latent heat of vaporization. Okay. Sixth is superheat temperature curves. So that I have showed you. Constant volume curves. I also showed you constant entropy curves. Okay. So this is another diagram. This time it is for R12. Okay, this is for R12. And okay, so we have seen. So we have seen in SI units. So this is in British units. Okay. So we'll just take a quickly review whatever we have studied today. So today's first we started with misconception about temperature. So whenever you feel cool or warm, that is related to its heat, rate of heat transfer, which indirectly relates to its thermal conductivity. So it's not about temperature, it's about heat of transfer. Then we saw the pressure enthalpy diagrams. Okay, so this was the simplest diagram. Then I explained you how to draw that pH diagram. In this case, we have used the temperature versus enthalpy diagram, but similar approach is used for pressures also. So after this, we saw that a little bit complicated diagram, which had this superheated, which had this constant volume lines, constant entropy lines. So this was it, constant temperature lines we have seen. So these are also called as superheated temperature lines. So we saw that term here, superheated temperature lines. So these are called as superheated temperature lines also because they lie on superheated region. Then it has a constant entropy lines, constant volume lines. Okay, so this was also a simplest diagram. Then I showed you the commercial, like what we use, that book. So this diagram I showed you. Okay, so this is available in that book. This is a pH diagram, and I showed you the table also. Okay, so I request you again to buy this book, and we saw some processes on it. Okay, so that's it for today. If you have any queries, please ask. Meanwhile, I will take the attendance. So any questions? Any questions? So just bear for a couple of minutes. I'll take your attendance and then we can leave. So it is taking attendance. Previously, I think it has not taken, but now I think it taken. Yes, so it has taken the attendance. So thank you all of you for joining the lecture. We'll see you next time. Thank you. So now this lecture is being concluded.